We're going to be doing notes and examples for 13.1, which is theoretical and experimental probability. So before we talk about probability, we need to talk about a few things. You're going to hear the word outcomes a lot as we go through our notes. Our outcomes are possible results of an experiment or a situation. You're also going to be working with a specific event. Event can either be a single outcome or it can be a group of outcomes. Our sample space is all of our possible outcomes. So we're going to be working with probability. Probability is a measure of the likelihood that an event will occur. So if the outcome in a sample space are equally likely to occur, the probability of the event is a numerical value from 0 to 1. It could also be from 0% to 100%. So either a numerical value from 0 to 1 or a percent value from 0% to 100%. And it measures the likelihood of an event. So there are actually 3 different ways. So we can write it as a percent, we can write it as a ratio, or we can do the decimal. This is simply where we divide the numerator by the denominator. And when we set up a probability, they're going to tell us some sort of event to work with, and it is our favorable outcomes for that event over our number of, our number of possible outcomes. So it's the favorable over the possible. So it's our favorable number of times our event occurs over the sample space size, which is all of our possible outcomes. There are 2 types of probability that we're going to work with. They are known as experimental and probability. In an experimental, we are basing our information on the results of an experiment. So they're going to actually tell you for our sample space the number of times that the experiment was done, and they're going to tell us within their recordings the number of times that our event we're wanting the probability of happened within that experiment. The other one is theoretical probability. So this describes a likelihood, and this one is based on mathematical reasoning. So it's what we know about our object itself. So how many sides, how many pieces, how many individual things are there? So when we go to get our numbers for this one, we're going to need to know the possible outcomes based on the object itself and its design, and how many of our event items happen within that. So experimental, they're actually going to give you data to work with, where theoretical, you have to use your known information about the objects to get your numbers. Complement of an event consists of all the possible outcomes in a sample space. So when we have an event and its complement, then our probability is always going to equal 1. So we have our original event, we have the complement of that event, and our probability for that is equal to 1. So we can use this fact to solve. So if we know the probability of the event and we want the probability of its complement, which is not that event, all we have to do is a simple subtraction of 1 minus the probability we've got. So let's look at some examples. So in this first one, we have a park has 530 trees. You choose 40 trees at random and determine that 25 are maples. We are looking at the experimental probability that a tree chosen at random is a maple tree. So we're trying to find the probability of having a maple tree. We're going to set up a ratio. You'll notice there's a second question. We'll get to that one in just a moment. So we start out with our number of possible outcomes. So this is how many trees did they actually go out and look at. So they looked at 40 trees. This is our total that they looked at. And then for our event, our number of favorable items, we're looking for maples, and they determined that 25 were maple trees. So we have 25 that are maple trees. So we're going to get this in decimal form. So we simply do 25 divided by 40, and our probability of this event is 0.625. So this is our decimal form. The reason I'm going to use the decimal form of my probability is because of the next question. My next question wants me to make a prediction. So about how many trees are likely to be maple. So in order to do a prediction, focus on what I'm writing. In order to make a prediction, we're going to take our decimal or fraction for our probability, and we're going to multiply it by the total number of items. So our probability is 0.625, and there is a total of 538 trees. So we have 0.625 is our probability times a total of 538 trees. And since we can't have just part of a tree, we round this and we get 336 maple trees. So our probability is our favorable, which is the 25 over the total possible, and they looked at a total of 40. We got that as a decimal. In order to do a prediction of all of the trees, we take our decimal or fraction value for our probability, and we multiply it by the total number of items. Okay. Second example. So we're going to be looking at different probabilities of the sum when rolling two standard number cubes. On a number cube, we have 6 sides, numbered 1, 2, 3, 4, 5, and 6. For the beginning of this, we're looking for the sum. So we're going to roll two number cubes together, and we need the sum for each roll. So we need to figure out our sum. So I made a little chart so I can calculate all of the sums that I could get when I roll two number cubes. So I have all of my possible numbers for the first number cube on the top and all of the possible numbers for the second number cube on the bottom. So if I go through, and my first number cube, I have 1, 2, 3, 4, 5, and 6. So this is my first cube. And then I have the possibility for what I could get on the second cube. So on my second cube, I have the 1, the 2, the 3, the 4, the 5, the 6. So we have three probabilities that we're going to work with. The first one is our probability of a sum of 9. So when we look at our list and we count, I have 6 rows and 6 columns of information. So this is my sample space. So when you count this, 6 rows and 6 columns, I have a total possible sum count of 36. So that's my bottom number. And now I'm looking for the ones that will give me a sum of 9. So I'm going to go through and I'm going to look for everything that would give me a sum of 9. So I know that 6 and 3 gives me a sum of 9. 5 and 4 gives me a sum of 9. 4 and 5 gives me a sum of 9. And 3 plus 6 gives me a sum of 9. So my probability of the event being a sum of 9, there are 4 different ones. And when we simplify this, we can write it as the fraction simplified, a decimal, or a percent. For this one, I'm going to leave it as a simplified fraction. For the next one, we want the probability of a sum of 2. We still have that same total possible outcome, so there are still 36 sums to look at. And when we look at this list of sums, and we're looking for the ones that would add up to make a 2, the only addition problem in this whole chart that makes 2 is 1 plus 1. Everything else is higher, so our number of items that have a sum of 2 is 1, and 1 over 36 happens to be simplified. And the last one, we're looking for the probability of a sum of 13. There are still 36 possible outcomes in our chart. So when we look at this, we have to be careful because in this entire chart, 6 plus 6 is our largest sum. And 6 plus 6 is only 12. That means 13 is not possible. So there are 0 sums of 6 plus 6 in our number cube chart. So our overall probability for this event, because it is impossible, is 0. So things that are impossible have a 0 probability. If it's guaranteed, it's a probability of 1. If it's impossible, it's a probability of 0. One more example with theoretical and experimental probability. And this particular one mentions the word not in it. So we're going to look at this one in terms of complements. So when we look at our information, a jar contains 10 red marbles, 8 green marbles, 5 blue marbles, and 6 white marbles. So the first thing I'm going to do is calculate the total. So 10 reds, 8 green, 5 blue, 6 white, and that makes a total of 29. This 29 is going to be the bottom number of my probabilities. There are 10 red marbles. So when I'm going to look at this, I want the probability of my event, which is going to be red. There are 10 red marbles, and we have 29 total. So now we're going to do the not red. So we're going to deal with our complement of the event. So the probability that it is not red can be calculated by taking 1, which is the total probability, and subtracting the probability of red. So our probability of it not red is going to be 1 minus the probability of red. So our probability of not red is 1 minus the probability of red. So, simple calculation, we're going to do 1 minus 19/29. So 1 minus 19/29, and I want this answer as a fraction. So 1 minus 19/29 as a fraction is 10/29. Oh, sorry. I have that backwards. My bad. This is 19, and this is 10. 1 minus 10/29 is 0.655, and we want that as a fraction, and it's 19/29. Okay, I will eventually have this written down correctly. 10, 19. There we go. Probability of red is 10 out of 29. The probability of not red is 19 out of 29. I apologize for those mistakes. Let's see if we can understand it. So we could have just added up all of the not reds and put it over the 29, or you can do the complement, which is the probability of that it is red subtracted from 1.